is Piotr Nowak from the Polish Academy of Sciences. Oh, and I don't have the title.
Spectral gaps, L2 Betti numbers, and coarse Baum-Connes.
Okay,
Yeah.
let's go with that one.
All right.
Yeah, so, right. Yeah, so we can talk about spectral gaps, L2 Betti numbers, and coarse Baum-Connes conjecture.
Thank you very much. I'd like to thank the organizers for the invitation here. It's wonderful to be here at this workshop. What I'm going to speak about is joint work with Kang Lee and Sanas Puya. So they were both postdocs in Warsaw, and this is something that we discussed. And this this has a subtitle that's a little bit more descriptive towards new counterexamples. To the coarse Baum-Connes conjecture. So I want to say right away that I won't, I don't have new counterexamples. What I would like to discuss, however, is how can one try to come up with such new counterexamples and a new strategy, or a strategy or a method for finding such counterexamples. All right. So let's start at the beginning. So the coarse Baum-Connes conjecture. So we start with Y, a bounded geometry metric space. And the Baum-Connes conjecture, the coarse Baum-Connes conjecture, is that the coarse index map from the coarse K-homology to the K-theory of the row algebra of Y is an isomorphism. This thing here is the coarse K-homology of Y, which you what this means. So PD is the Rips complex at scale D of the space Y, and then you take the direct limit as the scale goes to infinity, and the map lands in K-theory of the row algebra. So row algebras were defined yesterday by Federico. So this is not true in general. So if you take a sequence of expander graphs, and you take Y to be their coarse disjoint union, which means that we arrange the metric so that on each graph is just the graph metric, and then the two copies are the ith and jth copy are further and further away. Then this is a theorem of Hickson that so this is due to Hickson.
When you say such that, you mean that this is your definition?
Well, you just choose any metric that satisfies this, and on every graph. So there's some freedom, all you need is that the individual graphs are farther and further away from each other. So this is due to Hickson in 1998, and then Hickson, Laforgue, and Scandalis. So they showed that for this space, this map is not surjective. So for Y, mu C is not surjective. And there's an explicit K-theory class that they identified. So this is so it will be a class represented by the average projection. So this will be and so on each of these boxes, we put the averaging operator. So this is a projection, and expansion implies. So I'll call this P. Expansion implies that P tensored with, for instance, a rank 1 projection. P belongs to the row algebra, and its class is then not in the image of the yes. Thank you. So in general, So in general, I would require that, for instance, they come from a group which they're quotients of a group which is exact, which has property A, but we can. Yeah. Yes. Thank you.
So, sorry, I think
Yeah.
you should say logarithmic.
Say again.
Logarithmic because
Okay. I'm not sure if that's necessary. So what one needs is that, well, okay, so.
you don't need the group, sorry. Yeah.
I don't, yeah, so, yeah,
Okay.
yeah.
But then you said property, it will be, if it is property not free group, it will not be rational.
No, so if these are expanders that come from Kazhdan's construction, sorry, from the Margulis construction, so if they come from they're quotients of a residually finite group, then all I need is, or all that is needed is that the group is exact. That the group from which, of which they're quotients.
So then it will not be rational.
Yes, they might not be large card. Okay. Okay, this is so far the only counterexample, bounded geometry counterexample to the coarse Baum-Connes conjecture, and so there's a natural question. Does every counterexample. So is this the only obstruction? So does every counterexample to the coarse Baum-Connes conjecture have to contain expanders? So that's the question.
Piotr, are you tacitly assuming some kind of local bounded geometry and when you're thinking about this?
Yeah. So this is for a bounded geometry.
You're always assuming bounded
Yeah,
geometry.
yeah.
Okay.
Yeah. So without this, there are counterexamples due to Boolean with these large spheres, but they're for
Well,
injectivity.
not injectivity, but
Yeah.
probably you could turn them into search activity.
Yeah.
I assume.
Yeah.
Sorry.
Yes.
Contain. How?
Of course.
Yeah.
Okay. So let's go back to the motivation for how this. So this projection that we have here. So this is a form of Kazhdan projection, and what I'd like to discuss then is our Kazhdan projections in the setting of group cohomology. Okay, so G will be a group generated by a symmetric set S, finite, and F will be a family of unitary representations of G. And I want to define some completions, so some C-star algebras related to these families of representations. So these are so-called exotic C-star algebras, which lie in between the maximal and the reduced group C-star algebra. And they're completed in the norm related to the family of representations, and the norm is given by the supremum of the norms of images under these representations. So, for instance, if F is all unitary representations, then this is the maximal group C-star algebra. And if F is just the regular representation, then this is the reduced group C-star algebra.
Do you get if you take F to be all the representation fact with finite quotients?
Well, so you get some sort of C-star algebra, and it's not much known about these. So they lie somehow in between the maximal and the reduced. But they can have some strange behavior in between, for instance, in K theory.
Can identify it with some functions with finite completion, or it does not hold?
Maybe I don't know. Possibly. I don't think there's that much known about these in general.
Not really, because, for example, if the group were a manifold, then none of these differences would make a difference. You know, so they've been reduced and max, they're all the same. They're not the manifold groups too.
So there's a characterization of property T that goes back to Ackermann and Wolter in 81. G has property T if if and only if there exists a Kazhdan projection, so a self-adjoint projection in C star max, such that the image of this projection is the orthogonal projection onto the space, from the representation space onto the space of invariant vectors. So this projection is an important one. So this projection generates a lot of trouble when trying to prove statements in the form of various Baum-Connes type conjectures. And for instance, for a group with property T, this projection here can be constructed by applying the finite dimensional representations that you asked for. So taking a direct sum of these projections. So that's essentially that projection over there.
So for example, for SL3Z, what it will be? Like you take expand as a
Well, I mean, so the projection is always, for expanders, it's always that, right?
For SL3Z here, what do you do?
Oh, so you mean for the group?
Yeah.
Well, I mean, it's an element in C star max. It's a projection with this property. It's not explicit, of course, right? Yeah. Okay. So since this is a good source of these projections, then
For example, if you start with a finitely generated group and you take the C star algebra of it, isn't it of it? There is a natural candidate to take the sum of all the generators and their inverses, because these are it's like the fixed point of them.
No. So the way that you can generate this projection is what you can do. So what you can do is you can take what you're saying. So you can take the sum of the generators and average that. So you get a probability measure on the generators, and then you take convolution powers and take their limit, and this will be the projection. Okay, but what we actually want to do is we want to somehow generalize this, because these types of projections are well, in a way they also have some limitations and restrictions. For instance, this type of projection is always non-zero. Is non-zero only if this space of invariant vectors is non-trivial for some representation. Well, yeah, if you do the same thing with respect to a family of representations. So, for instance, in the image of this projection in the reduced group C star algebra, for instance, is always zero, simply because this space is trivial. So, so that's one thing. And so another thing is that this is a projection that lives in the algebra itself, and we're interested in classes in K-theory. And in K-theory, you have actually much more freedom, because you have, well, classes in K-theory are represented by projections in matrix algebras over your algebra. So in general, it might be beneficial to look at classes that are represented by projections in matrix algebras. So so let's rewrite this so that it's easier to generalize this. So this is the group Laplacian. So this is an element of the group ring, then the projection P, the projection P0 is the projection onto the kernel of the image of this Laplacian in a representation, which is isomorphic to the zeroth reduced cohomology with coefficients in phi. So this is the Hodge-de Rham composition. So if we look at it this way, there's a natural way to generalize this concept of Kazhdan projections. Okay, so now I will assume additionally that the group G has type Fn plus 1, which means it comes with a classifying space with finite n plus first skeleton. And my cochain space will be the space functions from the nth skeleton into a Hilbert space, and then codifferentials are represented. So they are of the form pi of dn, where dn is a matrix with group ring coefficients. And here ki is the number of I simplicities. Okay, so the Laplacian, the cohomological Laplacian, is what it usually is. So dd star plus d star d. And so this is also a matrix, a square matrix with group ring coefficients. And we have Hodge-de Rham, which says that the kernel of pi of delta n is the reduced group cohomology with coefficients in pi. Okay, so so in this setting I can define higher Kazhdan projections. So a Kazhdan projection in degree n is a projection Pn and it belongs to the matrices So here I will be doing things with respect to this family of representations. So I can have these Kazhdan projections in relation to a family of representations. So it belongs to the matrices over the appropriate C-star algebra, such that for every pi in this family, its image is the orthogonal projection onto the harmonic cochains. Okay, so let's start with some basic observations. So if we look at this Laplacian inside the matrices over the exotic algebra, so this so if this has a spectral gap, so that means that pi of delta n has a uniform spectral gap for pi in F. Then the projection, then Pn exists and belongs to this algebra. Okay, so this is just spectral calculus. Pn is not zero if there is at least one representation for which the reduced cohomology does not vanish. And when we look at the case of the reduced group C-star algebra, this reduces to the L2 cohomology of G. And I can compose with the von Neumann trace and then I get that for the class Pn and K0 C star F of G, this is just the nth L2 Betti number.
Sorry again to bother you, but I don't
Sure.
quite understand this statement.
Yeah.
If this is a spectral graph, then Pn is there. Pn is always there.
No.
The point is that
it has to be in the C-star algebra, right? So in the matrices over the C-star algebra. So in order to ensure that, you need to be able to do continuous functional calculus. So for that you need the spectral gap, right? So in general, if you don't have that, if you don't have the spectral gap, you will only be able to use the Borel functional calculus, which will take you out of this.
So you mean that there exists a Kazhdan projection, otherwise?
Well, so this projection will, so it's, if you think about the case of L2 Betti numbers, for instance, right? So just the case of the regular representation. This projection always exists, but it exists in the von Neumann algebra. So if you wanted to sit in the smaller algebra, which is the reduced group C-star algebra, it's guaranteed by the existence of the spectral gap for the Laplacian.
This PN is complete I of delta n?
This projection is the spectral projection onto the kernel, right? Onto the kernel of the Laplacian here. So does this answer your question, or?
I'm a bit confused. The star F is a sub-algebra or a quotient algebra of the star max?
It's a quotient.
Quotient.
Yeah.
So why do you say it's inside the sub-algebra? You said something that is in the...
No, so what I'm saying is that I want this projection to live in this in this C-star algebra, right? So it's a spectral projection associated to zero of this element.
You mean that it might be zero? So the point is that it's a non-zero element if you map it down.
No, well, so what I mean is that that it might live out, even if the Laplacian lives itself in this algebra, then the spectral projection associated to zero might live outside of this algebra. And the spectral gap guarantees that it actually lives inside, right? So the case of the regular representation is really instructive. So you take the Laplacian, and it's an element of the group ring, or matrices over the group ring, and its spectral projection associated to zero will usually live outside of the reduced group C-star algebra, because it will live in the von Neumann algebra, which is a much larger completion, right? So
there is no spectral.
second.
And because there is no spectral.
Yes, exactly. Yes.
And you have to think of the C-star algebra like being the space of continuous functions on some dual, and the von Neumann algebra being L infinity.
Yes.
You can do, even if you don't have a spectral gap, you can do the L infinity function calculus.
Yes.
If you want to separate, you need the identity to be isolated from the rest of the continuous function at 0 here and 1 there.
Thank you.
Okay, so let me state what we proved. So now I will additionally assume that this is residually finite, and I have a family of finite index normal subgroups whose intersection is trivial. And my space Y will be, again, this coarse disjoint union of quotients, G mod n I, with a similar requirement as before. And then I also want to look at, so the family, so now I need to also specify the family of representations that I'm interested in. So F will be the regular representation plus the representations lambda I, and lambda I are the representations quasi-regular representations of G on L2 of G mod Ni. So we just take G mod Ni acting on itself and view it as a representation of G. So here's a statement. If G is exact of type Fn plus 1, residually finite, if the Laplacian in the algebra associated to this family F has a spectral gap, then if the coarse Baum-Connes conjecture or coarse Baum-Connes map is surjective, for Y, then we have that for the groups, subgroups Ni, the Betti numbers of Ni and the L2 Betti numbers of Ni are equal for all but finitely many indices I. Okay. So the first remark is that that this is if this holds, then this is a strong version of Luke's approximation theorem. Okay, so I can rewrite this this equality here as follows. Okay, so I can pull out the index, and I get this. So this is 0. Now, Luke's approximation theorem says that if you look at this, then this goes to 0. So this gives if you have surjectivity of Baum-Connes, of course Baum-Connes, then you get this. Yes.
Do you want G on one of these in the statement of the theorem? In the statement of the theorem.
Yeah. No, that's yeah. You can rewrite this as right. So this is the index times the Altobetti number. So you can rewrite it if you'd like with G. Okay, so let me say a few words about proof.
What is exact?
So exact is the same as property A. So it's a geometric condition that is a sort of metric amenability. It says that basically you can cover your space with sets that are or with well actually that to every point of your space you can associate a probability measure, and the probability measures are uniformly close and at the same time have controlled supports. And so you can make the uniformly closed go to 0 and the supports then go to infinity. So it's a geometric condition that Goulian defined in the context of well, similar considerations, of course, Baum-Connes conjecture, and for his remarkable theorems on coarse embeddings and the Novikov conjecture. Okay. So there are examples of groups that are not exact. So there are these Gromov monsters that contain expanders, and then there is a stronger construction by Osaida. But they do contain expanders. There's also Osaida also has a construction of a group that's not exact but has the high group property, which is interesting. So yeah, but there's not many of them. I think these are the three cases. Okay, so let me say a few words about the proof. So the proof follows a strategy that's been used before, originally by Hickson and Hickson, Laforgue, Scandalis, and then this was also extended by Goulian and Rufus. And the idea is that you look at this is the so-called two traces argument. So there's a diagram that one considers. I'll write the diagram. So there's a lifting map that goes from the algebra C star Y into this algebra here, and then it induces a map on K theory, and then there are two traces that I'll describe in a second. Okay, so this this diagram commutes on the image of the Baum-Connes map. And under the assumptions that we have, the projection that we have lives here. I mean the class, the K3 class that we want to consider. And yeah, so let me maybe say what the two traces are. So this trace here is obtained by looking at this space as a disjoint union of finite spaces and just cutting down to each space separately, to each of these finite pieces. So this maps into the compacts of L2 G log Ni, coefficients in some auxiliary Hilbert space. And this takes an operator from here and assigns to it the product of restrictions to each box separately. So this is the projection. So Qi is the projection onto the ith box. Okay, so then D star on K theory goes from C star of Y, and if you apply the K theory functor to this, you get this. And then, so in particular, D star of this class Pn is a sequence of the sequence of dimensions of the harmonic cochains in these finite representations. Okay, and then the top map, this map T is on C star G, invariant with respect to the subgroup. So this is isomorphic to the reduced group C star algebra of Ni tensor the compacts, and so this is von Neumann trace tensor with the canonical trace on K, on the compacts. Okay, so yeah, and then we identify that if you compute what this is, then this actually is a sequence of, so the product of L2 Betti numbers. So this is more or less the idea, the strategy for proving this. Okay, so so the way I view this is mainly as a way of trying to find these new counterexamples. So we have tried to come up with new counterexamples using this. It seems quite difficult, and it's actually quite related. I wasn't here last week for Alex's talk on high-dimensional expanders, but this is actually very close, right? So, because what you're trying to do is if you try to use this statement to find counterexamples to the coarse Baum-Connes conjecture, then what you want to do is to contradict this statement, but at the same time you need to satisfy all these assumptions. So in particular, the spectral gap requirement, this is essentially this is very similar to this the setting of high-dimensional expanders, but here you just require the spectral gap to be in a particular dimension, not in up to a certain dimension. So there are examples. So what we do know is that there are examples that where you can have this behavior, but we can only produce them to show that this class of spaces where we can, for which we can use this particular statement to contradict the coarse Baum-Connes is not empty. So we can produce them using expanders themselves. So here's an example to show that spaces like this exist. So we take the free group, and this is a finite index family of subgroups with trivial intersection, such that the Cayley graphs are expanders. And we can take F2 cross F2 and family of subgroups Ni cross Ni. So we'll produce these using the Kuhn theorem. So from the Kuhn theorem, bless you. So these have a uniform spectral gap. By Lutz's approximation theorem, we have that so we know that the L2 Betti number of the free group, the first L2 Betti number is the free group on two generators is 1. So this goes to 0, which means that the standard Betti numbers go to infinity, again by the Kuhn formula. We know that this space, this group has non-trivial homology, and then again for the L2 Betti numbers, we have that first L2 Betti number of the product. This is 2 times the product of the first and the 0, and so this is 0. So we get a sequence of so we have the spectral gap assumption satisfied, and we have the L2 Betti number of the group 0, but the Betti numbers of the subgroups non-zero. So this violates this statement. So we tried for quite a while to produce examples that would be better than this. And so what I want to do is finish with this. I want to state what is needed and why. This could be useful. So what we're looking for is an example of a space Y. Such that for some large n, we have the following thing. So spectral gap of lambda I of delta n is uniform. The nth L2 Betti number of the group G is 0. The subgroups have non-trivial Betti numbers for infinitely many indices. And the most, so far, that thing works, but the most important condition is Y does not contain expanders. So the point of this is that this being a counterexample should come from a strictly higher dimensional phenomenon. So the philosophy is similar, but yeah. So arranging this this last thing is, of course, the difficulty. And maybe one last question. So if this works out as it's written here, then the space Y does not embed coarsely into the Hilbert space. Because if it would satisfy the coarse Baum-Connes conjecture by Bouillon's theorems. So the question one, the next question is one sufficient to prevent coarse embeddability into the Hilbert space. So if you have the spectral gap in some high dimension, can you embed into the Hilbert space coarsely? All right, I'll stop here. Thank you.
Thank you. I think we should have time for a couple of quick questions. So anybody? Yeah.
I remember the time when it came out with Make-a-Datum Noel, but it was always short of having a group which is a counterexample to the Baum-Connes conjecture.
Yeah.
What is the situation of that problem and what is really missing?
So this is the coarse Baum-Connes. So this is a metric version. So for this, there are groups that contain expanders, and then these groups also don't satisfy the coarse Baum-Connes conjecture. So for this version, for the standard, for the classical Baum-Connes, it's open.
And expander are not heavy.
No, so Higgs and Laforgan Scandalis.
The groups contains expander. They do not contain expander. The quotients are expander, and you build out of it a metric space, which is a metric space of expander, but
Yes.
they are not really part of the group. They are quotients.
Yes. Yes. So there has been this huge effort to embed expanders into groups specifically for this reason. So now there are these examples due to Damiano-Seidel, which contain expanders, groups, finally generated groups which contain expanders isometrically, certain families of expanders. And those, for instance, are counterexamples to Baum-Connes with coefficients. And that goes back to Hickson, Laforgue, and Scandalis. But the classical Baum-Connes without coefficients or with coefficients in C, that's wide open.
Right. I'm afraid we run out of time, so.
I'd like to make a funny comment.
All right.
Not mathematical. So this group containing expanders appears in a recent novel by a French author. It's not mathematical, a novel, which won a lot of prizes and was like million copies was. So million people knows about a group containing expanders.
Very nice.
I have not followed. What are these new examples containing expanders? Which group is this? Well, that I didn't understand your comments.
My comment is not mathematical. There is a novel by a French author.
It's a novel by a French author. Yes,
which won a lot of literature prizes, translated in 40 languages, and it's a science fiction thing. And part of it is really in a good language explaining the construction of a group containing an expander. So a million people knows about it.
I think on that happy
The
note,
anomaly, yes. And it's called the anomaly. Yeah, so it's really...
All right.
but it doesn't hint yet a counterexample to actual Baum's.
No.
All right.
I should mention that I didn't mention this, but there's a lot of the work leading to these new examples of groups containing expanders was also done by Gulnara as well.
Right, so before we thank Piotr again, Cornelia wants
I
to...
just have a quick question about the projection.
It's going to be a group photo announcement.
Oh, not a photo announcement. I'm really sorry. I thought it was, yeah, sorry. But that's good, because then I can ask my math question about the projection. I mean, do you have the same formula as in the classical case, that by, with a series of powers and multiple operators?
Not really, because these are matrices, right? So this is.
So you don't have any sort of
No.
way of building some sort of average operator? that
Not really,
operates
no.
powers and-
So there are more questions, so please ask Piotr after we thank him. And I think 5 minutes before the next talk, which is in now only 20 minutes, there will be a group photo just outside here. Am I saying it correctly? Alright, so you guys have 20 minutes to get coffee and then let's get pictures.